Welcome, cosmic travelers, to another journey through the mysteries of the universe. Today we're venturing into the enigmatic world of black holes, the universe's ultimate mystery. Black holes are cosmic phenomena that have long captivated our curiosity and ignited our imagination. They're the darkest corners of the universe, elusive and enigmatic, where the rules of physics as we know them cease to apply. They're the universe's best-kept secret, lurking in the shadows, silently pulling in anything that dares to come too close. Black holes are regions in space where gravity is so immense that nothing escapes its grasp, not even light. They are born from the remnants of massive stars that collapse under the weight of their own gravity. When a star exhausts its nuclear fuel, the delicate balance between gravity pulling in and pressure pushing out is disrupted. The star implodes, creating a gravitational field so strong that it engulfs everything, leaving behind a black hole. Imagine the universe as a grand cosmic tapestry with each thread representing the fabric of space and time. A black hole is like a tear in this fabric, a deep well from which no thread can escape. It bends and twists the universe around it, creating a vortex of gravity that devours everything within its reach. At the edge of a black hole lies the event horizon, a boundary that marks the point of no return. Once you cross this cosmic Rubicon, there's no coming back. The black hole's gravitational pull is so strong that it drags you in, stretching and distorting space and time in ways that boggle the mind. Despite their ominous reputation, black holes aren't just cosmic vacuum cleaners. They're fascinating laboratories where we can test our understanding of the universe and the laws that govern it. They're cosmic enigmas that hold the potential to unlock secrets about the very nature of reality. So, buckle up as we dive into the abyss of the universe's most intriguing secret, the black holes. As we journey through the cosmos, remember, the universe is a place of wonder and mystery, full of secrets waiting to be discovered. Black holes are regions in space where gravity pulls so much that even light cannot escape. The gravity is so strong because matter has been squeezed into a tiny space. So how do these cosmic enigmas come into existence? Well, the birth of a black hole is a cosmic spectacle of stellar proportions. It begins with a star, much like our own sun, but far more massive. Stars are the ultimate cosmic factories, fusing lighter elements like hydrogen and helium into heavier ones, releasing tremendous energy in the process. This energy exerts an outward pressure, balancing the star's immense gravity, which tries to squeeze everything inward. But there's a catch. This delicate balance can't last forever. After a few billion years, the star exhausts its nuclear fuel. Without the outward push of energy to counteract gravity, the star begins to collapse under its own weight. Now here's where things get interesting. For stars about 20 times the mass of our sun or more, the gravitational collapse is so intense that it crushes the core to a point of infinite density, a singularity. Around this singularity, a boundary forms, beyond which gravity is so strong that nothing, not even light, can escape. This boundary is the event horizon, marking the birth of a black hole. But what about smaller stars, you might ask? Well, they meet a different fate, transforming into white dwarfs or neutron stars, which are fascinating in their own right. But that's a tale for another time. So, in essence, a black hole is the tombstone of a massive star, marking the place where it collapsed under its own gravity, squeezing a vast amount of matter into an incredibly tiny space. This intense concentration of mass creates a gravitational field so strong that it warps the very fabric of space and time around it. Now, imagine space-time as a fabric. A black hole warps this fabric with its mass, creating a well that nothing can climb out of, not even light. Now let's delve a bit deeper into this fascinating concept. Space-time is the four-dimensional framework in which we perceive the universe. It's a blend of the three dimensions of space that we're familiar with, up and down, left and right, forward and backward, tied together with the progression of time. Now imagine space-time as a flat rubber sheet. If we place a massive object on this sheet, say a bowling ball, it would cause the sheet to warp, creating a dip or a well. This is exactly what black holes do to space-time. Their immense mass causes the surrounding space-time to curve so drastically, forming a deep well from which nothing can escape. At the edge of this well lies the event horizon. It's not a physical boundary, but rather a point of no return. Once an object crosses the event horizon, it is doomed to fall into the black hole. From our perspective, it would appear as though the object is frozen in time at the edge of the black hole, while in reality, it's being pulled inexorably inward. And this is where things get really weird. The closer an object gets to the center of a black hole, the more warped space-time becomes. In fact, at the very heart of a black hole, space-time becomes so warped, it forms what we call a singularity. A singularity is a point where all the laws of physics as we know them break down. Cross this, and you'll be pulled inexorably inward, where time and space behave in unimaginable ways. The event horizon of a black hole is truly the ultimate point of no return, a boundary beyond which the universe as we know it ceases to exist. It's a stark reminder of the unfathomable power and mystery of black holes. As you fall in, you'd be stretched and squeezed, a process whimsically known as spaghettification. But don't worry, this is just a simulation. Now let's dive a bit deeper into this tantalizing term, spaghettification. Picture this. You're falling into a black hole. As you approach the event horizon, the bottom part of you, closer to the black hole, begins to feel a stronger gravitational pull than the top part. This difference in forces begins to stretch you out, much like a piece of spaghetti, hence the term. But it doesn't stop there. While you're being stretched vertically, you're also being compressed horizontally. This is due to the black hole's immense gravity pulling you inward from all sides. You're now a long, thin strand of matter, spiraling down into the inky abyss of the black hole. This might sound like a scene from a sci-fi horror movie, but in reality, the process is so fast and so extreme that you wouldn't actually feel any pain. Instead, you'd be torn apart at a molecular level before you even reach the event horizon. And here's a mind-bending fact. From an outsider's perspective, you'd appear to be frozen in time at the edge of the black hole, gradually fading away rather than falling in. Despite their dark reputation, black holes aren't completely black. And as we'll see in the next scene, they also have a faint glow. They emit Hawking radiation, named after the legendary physicist Stephen Hawking, which could eventually lead to their evaporation. Yes, it's true. Black holes, these voracious cosmic monsters, aren't as black as they seem. They emit something called Hawking radiation, a concept proposed by none other than the legendary physicist Stephen Hawking. Hawking radiation is a theoretical prediction that black holes aren't entirely black, but emit small amounts of thermal radiation due to quantum effects near the event horizon. Now, this isn't your typical radiation. It's the result of a fascinating interplay of quantum mechanics and gravity, two fundamental forces of nature. Here's how it works in a nutshell. Quantum mechanics suggests that particles and antiparticles constantly pop in and out of existence in pairs near the event horizon. Occasionally, one of these particles falls into the black hole while its pair escapes, stealing a tiny bit of the black hole's energy in the process. Over unimaginably long stretches of time, this could lead to the black hole losing so much energy, or mass, that it completely evaporates. The implications? Black holes might not be eternal, they might have a lifespan, albeit one that's beyond human comprehension. Moreover, Hawking radiation could be a key to understanding quantum gravity, a holy grail of modern physics. Black holes challenge our understanding of physics, raising questions about the very nature of reality. And isn't that what makes exploring the cosmos so irresistibly captivating? They remind us that the universe is a place of wonders, waiting to be explored. As we've journeyed through the enigma of black holes, we've delved into their birth from collapsing stars, stared into the inescapable abyss of the event horizon, and experienced the mind-bending phenomenon of spaghettification. We've even caught a glimpse of the faint paradoxical glow of Hawking radiation, hinting at the potential evaporation of these cosmic behemoths. Black holes, the universe's ultimate mysteries, challenge our understanding of physics and push the boundaries of our imagination. They're a testament to the extraordinary depth and breadth of the cosmos, a frontier that continues to beckon us. As we continue to explore this frontier, who knows what other wonders we might uncover? If you're intrigued by the abyss of black holes, give us a thumbs up, and don't forget to subscribe for more astronomical adventures. Until next time, keep looking up.